set up to record. Okay, well then to finish off our chapter 3, if you recall, chapter 3 has really been in the investigation of how we go ahead and either model our data or our application logic inside of a system, right? So up until this point, we looked at how we store primitive data. We went and then examined how we then store and access and invoke our procedures. That's where we left off last class. So the next thing that we're going to examine before we kind of finally bring this to a close is going to be, how do we take more complex data in the form of, say, arrays or structs, our structures, or we'll introduce another concept called unions, and how do we go ahead and implement those at our system level? And so I think one nice thing about this particular portion of the chapter is it's going to be a lot of it'll be a lot of concepts that we've discussed when we looked at the essential C. So we already defined a lot about what arrays and structures are, and you'll see the way that we go ahead and access them, the way that we model them, the way we implement them at the system level is probably going to be something that's intuitive to your understanding from where we're at currently. Okay. So with that said, just a quick overview of this slide. We'll break it down into effectively our array basics, which you probably already familiar with in C. But the interesting thing that we'll really take examining is, how do we take our arrays in C and how are they therefore implemented at the assembly level, right? Like what are the instructions? So keep in mind, any instruction that we encode in C has an analog set of commands and assembly. But the thing about assembly is that it has a set of registers that are bound to some keywords when we go to compile our C code. So we're going to look at some of these registers that are used when we declare, say, for instance, an array, or when we try to access an element from the array, so we know what's happening underneath the hood. So we'll talk more about the array basics, and we'll examine both C code, optimized C code, and then our assembly code for that. We'll also go ahead and take a look at pointers in arrays, because there's a close correlation between when we declare an array and the concept of a pointer. They both have to deal with memory addresses, right? So we'll take a look at our pointers in array and just hammer in those similarities. And then we'll look at concepts related to compiler optimization. So when we take our source code and then when we tell GCC to compile that for us, what is it doing? How is it going to change our source code into optimized C code, which then gets translated into our assembly code? Okay, and again, just to ensure that we're all on the same page, we're in a strongly typed language. So when we start looking at any of the mathematical notation, we're going to define our data type as T. We'll define our array as A, and the number of elements that our array can hold will be N. And so very commonly then, the general form of all of our array declarations in C is in this approach. And so if I want to state what is the starting location, when we start looking at tables and whatnot, just so you're familiar with some of the notation that you'll see inside of both the book and the content of the slides, then if you see X sub A, that's going to be the starting location of the array. And so when we go ahead and declare an array, the allocation in memory would be based off of L, which is going to be our length, and N, which is going to be the number of bytes for each of our data types in T. And again, these are concepts we've talked about before. We abstract a lot of that away initially in C, but we haven't abstracted that away in assembly when we were talking about that in a prior chapter, right? So again, concepts that were already, these are expressions we've already seen. Obviously, then our elements will have index numbers between 0 to n minus 1, which is going to be the offset in our memory address. And then finally, if I wanted to compute an ith element address, I can take whatever my starting position is, and I can add to it whatever my whatever index value I'm going to get times my L value here. And we'll talk more about that inside of code when we get there. So again, we've seen this before. Let's reiterate. This is just some common ways we can declare arrays. Now notice I have a combination of things here. I'm using a character. I'm using a character pointer. I'm using an integer, and I'm using a pointer to a double, right? Pointer double array. Okay, so based off of your intuition, so we know that this is, looking at the box notation, that holds up to 12 elements, right? So we know the length of this array. What is the byte size of a character? 1. Very good. So we can compute the total number of bytes that would take, right? So what is the byte size of a character pointer then? If this is 8 elements, what would be the data type size? What is the size of our T? Well, let's jump to the table really quick, and then I can just do the correlation instead of doing a quiz-like approach. Okay, so let's go here. So we've seen this first element. We see, yeah, the element size is 1 and our total size is 12, right? Now notice with our character pointer, it's going to be 8 as opposed to 1. The question is, why is our element size for our character pointer 8 as opposed to 1? Like, is that an obvious question for everybody? So when we're talking about this first array here, we're talking about the value that a character can have. So when we encode a character with some kind of bit sequence, the number of allocatable bits in any character is 1 byte, which is 8 bits, right? So 1. So my element size is, for every element inside that array, it consumes 1 byte. And of course, I have a total of 12 elements, so it's going to be a total size of 12. Okay, so here, a character pointer is going to be an address to a character. My addresses, since I'm in a 64-bit environment, are going to be 8 bytes. So anytime I have any pointer, all my pointers, since they reference addresses, are going to be inside of a 64 addressable space. So is it more obvious now where that element size of 8 is coming from? Okay, so since we know that a character pointer holds addresses, it's going to be 8 bytes. And then we can look at the number of addresses we can hold, 8. So there's going to be a total size of 64 of contiguous memory that then gets reserved for our array. Kind of continuing this concept, if we have an integer, we know that integers have a bit sequence of 4 bytes, right? 32 bits. So we can say it's going to have an element size of 4. And if we have 6 elements, we just do that multiplication, say the entire space that's going to be reserved for this data is going to be 24 bytes then. And then finally, we have a double pointer array. That's going to be the same as a character pointer array, right? All of our addressable space is going to be 8 bytes. It's 5 elements times 5, so there's going to be a total of 40. And so again, if we wanted to express these in terms of a mathematical notation, we would find that on the last column of this table. And this is pulled, again, directly from the textbook. Does anyone have any questions about this? Or okay, so again, the entire the thing that drives this, though, is that we have this x86-64 architecture that effectively allows us to map this notation that we've become familiar with into principles that then go ahead and work at the assembly level. So some things we should be aware of. So let's look at how we can address the computation with our memory access here. So for an integer array E, so suppose that we have E, its its address register, whenever we go and reference E inside of our C code, will move into the register RDX. So that's going to be where our address space is. And then the index value, where inside of E are we going to then access a value, will go into RCX. So there's two different registers, right? And it makes sense, like the indexer is kind of like a counter. We use RCX typically as our counter register, and RDX is our destination. It's like one of our parameter spaces that we are typically pretty familiar with. So the notation from C then maps when we go to compile this into these two register spaces. Okay, so then when we have our instruction to be able to compute the address given the formula we looked at, now remember, in this instance, we're going to say that X sub E is the starting position of our address E. So we already stated what that was. I is going to be the index value from inside E we want to access. So what is this for here? What do you suppose this for is? Before we were using alias terms. Now we're using the actual value. But do you recall what the for is? If this were, what is E? Exactly. That's right. So this is an integer array. So that's the amount of bytes required for that data type. So clearly, our expression is given the starting position plus the number of bytes times the index into the address. We will get some result, and we're going to read that memory and compute the address, and then that address then goes into EAX. So those are going to be the three registers we're really going to kind of care about in terms of how we access and load data from our array into our register spaces. And of course, the scaling factor, when we talk about scaling factor, we're talking about scaling in terms of our data types. So the data types that we're going to be concerned about are either going to be 1, 2, 4, or 8. And that scaling factor is really going to be expressed on this term of 4 here. Okay. So what does the assembly level code then look like? This is effectively what it would appear to be then. So here we would have a move long, L for long. And then those registers we talked about was RDX, RCX. RDX has the starting location of our array. RCX is the index value we want to access. 4 is the scaling factor of the data type that we're using as an offset. And then finally, we're going to move whatever the result of that is into EAX. So again, taking those concepts we stated and just very quickly and rapidly throwing that into our assembly level instruction. Okay. So that's the basics of how arrays are kind of governed at the assembly level, translated from our C into our lower level. Let's just briefly mention pointer arithmetic. Now, we've already looked at pointer arithmetic in terms of C syntax, but let's just go ahead and harden our understanding of it with now our systems level understanding of how data is managed at the lower level. So again, C allows us to do arithmetic operations on pointers. When we do arithmetic operations on pointers, there's certain rules that when it sees that it's a pointer, it follows. It computes the value that is scaled according to the data type. So recall that when we go ahead and add to a pointer, we don't have to multiply to the index value the scale value. It already knows because it knows it's a pointer to a car, or it knows it's a pointer to an int, or it knows it's a pointer to a set of pointers. So what does that mean? Let's actually look at code. Let's just drop into our a sample application right here where we'll go ahead and declare an array of 5 elements. This is an integer array, and it'll just hold the values 10, 20, 30, 40, and 50. So here I'll create a pointer to an integer pointer, but it's uninitialized. So right now it does not point to any meaningful address. Then I will assign to P the address of effectively the starting element of our array. So notice here, I can just go ahead and pass array, which is an alias to the address of element 0. And so now when I do pointer arithmetic, this is a pointer. I can add to it the value of 2, which is effectively my index term. And now notice, since it knows it's a integer pointer, it does the multiplicative property of knowing how many bytes the bit sequence of an int requires, and then it will automatically then advance to be pointing to the element in the address space of our array at index 2. So if I were to dereference this, if I was to use my star operator in front, I would actually get the value of 30. Okay, so just to highlight, you can use the ampersand to get the address of an object. You can use your star operator to dereference a pointer, giving the value at that address. And there's a way to kind of cross between your pointer arithmetic expressions and your box notation expressions. So for instance, an array reference of a box notation I is identical to using pointer arithmetic encapsulated in parentheses and then using the star operator in front of that. In fact, if it's my understanding, if I remember correctly, and don't necessarily quote me on this, but if I recall some of the historical context of this correctly, one of the things that propagated your box notation was because of the amount of parentheses required for your arithmetic, your pointer arithmetic. Pointer arithmetic predates box notation on how we access elements in the array. And you could see how you'd have to do your arithmetic. It's the fact that it's a postfix operator versus a prefix operator. So to ensure that your prefix operator operates as a postfix operator, you have to use parentheses, right, to be able to do the expression inside, and then go ahead and do the star operation after that. And so this can get very cumbersome in the amount of parentheses you have to go ahead and provide. And so because of that, this became an alternate solution when C was being developed way back many years ago. Neither here nor there, but if you wondered which came first, it was the pointer arithmetic. And then because of how verbose its expressions can get, it motivated a new solution, which is the one that is more commonly thought of today, right? Our box notation. In fact, a lot of languages don't give you access to pointers like C does, right? Like Java has abstracted that away. Many scripting languages like JavaScript, Python have kind of abstracted those concepts away as well. Okay, let's see here. So in terms of expressions involving arrays, because now that we're talking about pointer arithmetic, once you start talking about arithmetic, you can create expressions. So when we have our assembly code translations, it's important to know that you can either do 4-byte or 8-byte operations. The reason why you should know that is for how much of your register is going to get consumed. So if you're doing some kind of operation that the return array that involves the values that go into your array, typically those are going to then use 4-byte addressable space in your register space, because that's like the amount of bit sequences that's consumed by ints and floats. Or even if it is like a car, you can still hold the car value in EAX, for instance, and you just care about the lower bits of that sequence. It's typed. You don't have to manage that directly, right? It's managed for you. And then if you're doing anything in terms of operations on pointers, then obviously that's going to be an 8-byte operation, because we're in a 64-bit environment and addressable space. So then we're going to start looking at our quad words then. Okay, so let's take a look then at this table based off of everything we had stated and see if we can't kind of understand the expression versus what actually operates underneath the hood with this expression. So let's start with this first. So remember, we said we were going to have an integer array called E. So when we just have E, the data type of E we should think of is going to be an integer pointer, right? Because it's pointing to the very starting memory address of where our array resides in memory. Our value that we would express this as mathematically would be as our x sub e. Sub doesn't quite work well in a text in code editors, so you'll just have to assume that the e that follows is a subscript. So our assembly code then for that is we would move into RDX, RAX. And then so here what we're just doing is moving our address of E into our register space. Okay, what about E box notation 0? When you see that, again, intuitively, the data type you should think of is actually int value, right? The way we would express that then is the memory. And notice we're going to do a box notation when we kind of define this in kind of a mathematical sense. So whenever you're seeing M, you could think of this as what resides in memory at this memory address. So you can think of it as a memory lookup. And then what we do here, the assembly code, recall that we can wrap in parentheses our register, so we use it as a dereference operation at the assembly level. So instead of getting the memory address and moving that into RAX, we can go ahead and we can dereference it and then move that value into our register space. So that's going to move our first element of E into our accumulator register. Okay, so again, if we wanted to index at some index value I, we have that expression we talked about. Let me not skip. For dereferencing, we're using box notation, so the data type is still going to be consistent. Where anytime we do a lookup using box notation, we're going to get back an integer data type. The expression we then use, since this is now not the 0th element, will be the expression that we showed just a couple slides ago, right? It's going to be starting at the memory address of E plus whatever the index value is times the amount of bytes our bit sequence takes. And so here, then, the assembly instruction is the same one we saw in the prior slide. And of course, we already know what this operation is doing. It's doing effectively the same operation as the one right before it. Okay, this operation here. The ampersand, as you recall, returns the memory address. So if we use box notation at index value 2 would normally provide the value from memory. But if we if we prefix it with the ampersand, instead is going to return the address. So when we see this, we can say, oh, the data type is going to be an integer pointer in this instance. If I wanted to go ahead and express that as a value, then I can go ahead and simplify it to being my starting memory address plus 8. Because it's index value 2 times 4. And again, we can now then see that we can go ahead and inside of our assembly code, use load effective address, and then we could go ahead and say offset by 8 on RDX and move that into RAX. So notice here we've actually deviated from using the move command when we were just looking at our index 0. When we're looking at the starting index, that was fine. But once we want to index further, that's when we would start using load effective address, because then we can define an offset of where we want to offset from. We want to offset by 8 bytes. So then we can give it the starting value, which is going to be RDX. That's where the starting point is. We offset by 8, and then we're going to move that into RAX. Okay. Here, we're going to do pointer arithmetic now. So recall, E is a pointer. Every time we have declared just an array, and we're not using box notation to index the value out of it, that's our starting location. So what are we doing here? We're going to take our starting location of our array. We're going to do some arithmetic, some pointer arithmetic to advance it to some index value of I. So if I were, say, for instance, 4, it would advance it to the 4th element. But now notice I will then subtract 1 from it. So this is then going to be the element before I, right? And because pointer arithmetic takes into account the byte size, it's not the byte in front, it's the full element in front, which means that, of course, pointer arithmetic always returns back a pointer value, a memory address value back. So the data type that we're going to get back here is going to be, in fact, an integer pointer. And again, since we're now doing offset on an address, the equivalent assembly code for that is going to be not dissimilar to the last one, where we're going to load an effective memory address based off of some offset. And then here, we're going to have, remember, our star operator allows us to dereference a memory address and get a value back. So if we take a similar notation with our pointer arithmetic, encapsulate it around parentheses, prefix it with a star, then the data type we're going to get back is going to be an int. And so here, this is going to be a memory lookup, right? So we'll have that expression, our starting element plus the number of bytes times whatever the index value is, minus the number of bytes and values we want to go backwards in. Because with pointer arithmetic, we can do both addition and subtraction. And it does the same, like 3 times 4 is 12. Okay, so here is probably the most interesting one that's different. Notice up until now, we've been talking at length about an array named E that contains integers. Notice in the table that this expression is going to return back a long. We're going to look ahead. Before we look at the expression, I want to highlight this is returning a long value. Okay, so what are we doing here? We're going to take and we're going to use the indexer. So we're going to take E, we're going to use box notation and put in our index term, but then we're going to put the ampersand. So we're not returning back the value, but we're going to return the memory address of that location, right? So that's going to be one memory address. And then we're going to do pointer arithmetic to subtract from it the starting position. Okay, so Does everyone understand what's happening with this first portion of this expression? That's an address, right? Everyone sees that's an address, and that's the address of the where element I is at inside of our array. And then everyone sees that this is just E, so that's the starting position. It's also an address. So when we subtract one address from another address, why do we get back along? That's right, yeah. So what we're doing here is we're finding the offset between the position, the address at I, at the ith element in our array, and the starting position, which actually returns I. That actually returns our index value, and our index value is indexed as a long value, right? It's a 8-bit indexing term because that's how big our addressable space is. Okay, let's move. Okay, let's move away from that. Okay, so we talked about arrays in length. We talked about arithmetic, pointer arithmetic, and we showed how those kind of correlate and how they translate, more importantly, into the underlying assembly code. Let's talk a little bit now about our nested arrays. And so we've seen nested arrays in C, which are effectively just arrays of arrays. So in this instance, we will create a nested array A that can hold integers. The outer array is how many rows. We do this in row major order. So our term of 5 defines how many rows is inside of our array or our outer array. And our inner array is the number of columns we have. So when you first learned about multidimensional arrays in Java, did you cover the power, how powerful the expressiveness is of being able to define different values of your outer and inner array? If it's a set of nested arrays, because then we can create effectively an array that holds pointers to other arrays. Now, right here, we're declaring these simultaneously. So that means that all 5 of my arrays, all 5 of my rows can have 3 columns. So this is going to create something that's more similar to tabular data. If I did an assignment into each one of my rows with a different length inner array, that creates a jagged 2-dimensional array, which is a very powerful concept. There are often times where you want to create something that's multidimensional, but it's not tabular, where you can have different numbers of columns for each row. So I just like to highlight that's one of the powerful concepts of thinking of it as arrays of arrays as opposed to a 2D array. A 2D array kind of is implicit of tabular data. And one of the limitations of tabular data is that you have as many rows as whatever the maximum number, you have a number of columns equal to the maximum amount of columns across any of your rows. Okay. There's another way we can declare this inside C as well. We can use a type def, right? So don't want to do that. So suppose I do my type def of row 3 underscore T. So that's defining each of my rows as having 3 elements. And then I can create an array of these, and that also creates a nested array, right? So this and this produces the same or similar kind of thing. Okay, and again, we can easily compute this, right? Our expression is given the number of bytes it takes for an integer times the number of row elements, now times the number of call elements, means that the amount of memory that will have to be reserved for this data type is going to be 60. So we can just extend the expression we've already learned to naturally include multidimensional arrays. And as we keep adding a level of nesting, we can just keep adding a multiplicative property. So the math kind of fluidly scales out nicely. And if we wanted to see how in our memory address it's actually being blocked off, and I think we kind of examined this a little bit in Lab 0, right? When you looked at the performance differences between iterating over an array using ij versus ji, you could see why one is more performant than the other. So if we actually look at our row, and as we said, this is row major order. When we talk about row major order, we could see at our box notation 0, right, we would have all of our column elements contiguously in memory. So at index 0, at column 0, at column 1, and column 2 would be our first 3 elements if we were to walk across this array just using pointer arithmetic. And then if we want to advance to the next row, that's going to be here. And then the next row and the next row. So each row is going to have 3 elements, which are effectively our columns, worth of values in between. And again, if I wanted to look at the address space between 0 to 60, as we stated, we can see I can do this as a arithmetic expression on my pointers to be able to dereference any one of these values inside my multidimensional array. So you could see we can be very efficient for looking up nested data if we know how to go ahead and lay it out inside of memory, either through walking across it, right, using box notation, or whether we want to use an arithmetic expression to be able to access that memory address. Okay, so if we just wanted to see what does the actual assembly look like in order to do that, it's going to be not dissimilar to what we've already seen. So again, our starting location of our memory address is RDI. Now, what's important is now we have 2 index terms, right? Once we start talking about multidimensional arrays, we have our outer and our inner. So inside of I, in this instance, RSI will hold our I term, and then RDX will hold our J term. Oh, wait, yeah. So if I wanted to go ahead and say, for instance, compute and dereference, I would operate off of those registers to be able to do such. And when I say that, I'm saying this is what C translated to assembly does, right? If we're working at assembly, we can do whatever we want. But when you're using double box notation, these are the registers that are being touched. Okay, let's move to fixed sized arrays. We already talked about what the hashtag define uses, and whenever we have anything that's supposed to be a constant value, we've learned we should use that preprocessor operation, right? And so this way, we can create an alias in our code, n, that could be whatever that fixed value is once we go and compile and execute our code. So again, use this notation. This particular notation is going to create a equilaterally sized array, right? The rows and columns are going to be the same. And the nice thing about using our constants for array dimensions is, again, for maintainability and consistency. Okay, let's look a little bit at how we could go ahead and define a function in C, a common C function, and we'll look at how it gets optimized and then how it gets converted into a symbol. So suppose that I have this function that works on that fixed. Okay, so here we defined our fixed sized array so that we can create a function for matrix product multiplication, matrix product element multiplication. So as you might be aware, if you've taken linear algebra or aware of linear algebra in any way, there's a lot of restrictions on how you can multiply one matrix to another. So if our matrix has the same number of rows and columns, that's much easier. Hence why we're going to define it on these fixed size matrices of n by n size. Okay, so with that said, we have our fixed product of element function. It's going to take in a fixed matrix that we, let me go back up so we can recall the actual, here we go. We created a type def here. I kind of did not explicitly state this, so let me explicitly state this. So I said we were going to create that constant value of n, a 16, and we were going to type def a fixed matrix of size 16 and 16, whatever we've defined our n's to be. And that's going to be a fixed matrix that holds integer values. Makes sense because we're going to do multiplication on it, right? We're going to do some linear algebra on it. Okay, so now that we all know what that is, we now have our type def terms here in our parameter. So we have one fixed matrix. We have another fixed matrix. And then we're going to have our index value in particular that we want to grab. So our index value of I and our index value of K. So here we're going to create a J term. We'll set our result to 0. And then so long as J is less than our fixed sized array, we'll iterate across J, and then we're going to grab that row and that column. So I and J are a particular row and column that we're going to multiply, create the sum, and deliver. That's how we do that in linear algebra, right? So this is just a basic kind of operation where we're actually modeling a numerical field using our array and creating an operation that produces a meaningful result. So how might this look then based off of compiler optimizations? And so here you can see our, oh, don't do that. You can see our header looks the same, but now you could see we're going to go ahead and get some, grab some pointers, some integer pointers in order to optimize this. We'll set up our result to be 0. We're going to do a do while loop because that at least optimizes where you're not even checking for the first condition, right? You're going to execute the body and then check the terminating condition. Then what we'll do is we're going to use those pointers to go ahead and multiply and get our result, right? So we're going to dereference those values, multiply them, append that to our result, increment, because we can do pointer arithmetic, it naturally advances across our arrays. We'll do our pointer arithmetic for our rows and our columns. And so since we know how two-dimensional memory is now stored in row major order, as we advance a row, we can just, as we advance across a column, we just increment by 1. As we advance across a row, we have to skip n number of elements to get to the next row. So if you're wondering what these increments are, you have to do if you're going to optimize it, you have to do them in those order. And then once your pointer gets to the end, right? Once your B pointer here gets to, or so long as it's not the end. So when it gets to the end, you're done your loop, and then you could return whatever the sum is. So notice this is doing the same kind of computation, but when we compile our code, it highly optimizes it to run it as quickly as possible. Again, the reason to kind of highlight this is compilers are very complex pieces of software that you can implement things that logically make sense to you without having to spend the brain power of optimizing it for the machine. Because trying to optimize code like this, you could accidentally, say for instance, increment B and then add to A, N, and then all of a sudden you're going to get an erroneous result. So it's kind of nice to know that your code is sometimes more performant than you write it because of what the compiler does to it. And then finally, what happens then is once it optimizes, so there's the optimization step, and then you have your step that translates it into your assembly. I'm not going to go into detail. I'm just highlighting that there's a linear path that goes from our code to this. Okay. And then finally, we don't always have fixed sized arrays. We start with the concept of fixed size arrays, and we're going to motivate that to be our variable sized arrays, right? Where instead of being able to type def with just n and having that fixed, suppose that we have our variable size, which I might skip because I might have grabbed the wrong code. I'm looking at the parameters, compute fixed matrix product. Fix, yeah, I think I duplicated my codes for this section. You get to, but I'll just state this. If you go and check this particular subsection in the book, the extension, there's a natural extension from our variable sized arrays to our fixed size, from our fixed size arrays. Just like there was a natural extension from our nested arrays from just our core array concept. Okay, so now let's move away from arrays and talk about the other more complex data structure that we've really utilized inside of C. And that's going to be our structures. So structures in C kind of group these concepts of objects together where we can have multiple fields that can represent, that are different data types. So arrays make sense when you have a collection of related values, like say, for instance, grades. Structs make sense when you have a collection of related values that aren't the same type of thing. Like say, for instance, I wanted to go ahead and model a person as a name and an age and a lot of other properties that are all consistently coherent for that model, but use differing data types. Then I can lean into a struct for that, right? So just like arrays store our data values in a contiguous block of memory, our structs do the same thing. Our structures are doing a very similar thing, but it's going to produce some byte offsets in order to do that, in order to compensate for the different sizes of our elements. So let's take a look at a structure really quick. Suppose that I have this structure rec, a record, that holds an I, which is an integer, holds a J, which is an integer. It holds a array that an integer array that can hold 2 elements, and it has a pointer to an integer pointer p. So if I were to look at what my structure looks like in memory now, I can visualize it the same way I kind of visualize an array, but now I can see that the block sizes are going to be different, right? So here I have my I have my J, I have my array element at 0, my array element at 1, and then I have my pointer, right? Any questions? Or does this kind of naturally make sense? So you can see here, then my total size of the structure is going to be 24 bytes. So when I go and use the operators inside of C that give me access to the fields defined inside of my struct, we can see how that offset, how that memory addressing works, how effectively that arithmetic works. So let's take a look at some of the codes, the code snippets here of what's happening from our C code, which is inside the comment to the actual assembly code. So suppose I have my record R, and inside of there I want to index I. Then I'm going to go ahead and dereference from RDI, which is my memory address of where the structure is at, and then I'm going to put that in my accumulator. Now I is effectively like my 0th element. Now suppose I wanted to get J. Well, the way I'm going to load J is going to be using my offset. So my offset to J is going to be 4 bytes. So from 4 bytes from RDI will be the next element. So notice the same way I can access the various values from an array I can do to access my structures. There's a very close tie-in conceptually of how this data is being preserved inside of our memory and how these operations do that for us. Okay, so suppose that we had, okay, let's see here. So we have our I, we have our J. So we have the same layout here, and we're just extending this. So from J, I, we already saw both of these. So here, this is going to be an implementation of if we wanted to go ahead and then get the memory address of the term inside of our A where this occurs. And so again, you could see we could just load an effective memory address up to 8, which is going to be where our array is at here. And then once we do that, notice this is the operation of actually loading a memory address like what we saw in the prior section. So here, what's happening, this looks complex. It's because one of these is loading to the array from the structure, and the other is loading the launch point of our array so that we can start indexing into those elements. Okay, so kind of the last thing I kind of want to mention, at least with the more complex kind of data types, is this concept of a union. And so a union allows a single object to be referenced according to multiple types. All the fields in a union reference the same block of memory. You can almost think of a union, I would think maybe in Java terms as maybe a singleton type. So for instance, inside of our union, you could see we can declare these two different, this structure and this union in a very similar way. We're just changing the keyword, but where we were recording, where we were summing up the number of bytes it takes to go ahead and set this structure, which would be 24. The size of our union is just computed by the largest member of the union. So it would just be 8, which would be the memory address here. And again, the advantages of unions are it reduces your memory usage when fields are mutably exclusive. You can bypass the C-type systems, but it can lead to bugs due to type system bypassing. And then they have some examples. I'm not going to spend too much time talking about unions, though. Just as a reference point, we're going to talk about them. And so when we talk about these structures, though, one thing we should highlight is how do we go ahead and align them? How can we do data alignment so that our computer systems can produce restrictions on some of these addresses? So the idea behind alignment is we want to be as efficient as possible for looking up memory. What does that mean? Well, baked into our pointer arithmetic, there's an idea that the amount of bytes consumed by each element is set, right? If that's not set, think about how much more complexity that brings into looking up a memory address. If it might be 4 bytes for one instance, but then the next is going to be 1 byte and the next one's going to be like 2 bytes in size, right? All of a sudden walking across and finding an element that might be 16 spaces over isn't simple, but it could be simple. What's a good way to make that simple? You just produce offsets. So inside of our structure, you look at whatever the encoding is for the largest element, and then every element is padded such that they consume that space. Does that make sense? So like in the other structure I had, since I had a pointer, that requires 8 bytes. Let's say I have a character, 1 byte. Well, I'm going to pad 7 bytes on that character so that my arithmetic pointer works the same way it would for an array. So when we're talking about data alignment, that's all I mean to mention.
That's not memory efficient.
No, but it's performance efficient. Yeah. That's right. And so just a good way, and you can see a good way we can go ahead and kind of highlight that is just like this right here. So if I had my I, and then say I had this character, then what I can do is I can offset this character. I can align the character to be the same amount of bytes as my I, so that instead of having to know to increment from by 4 bytes, then 1 byte, and then 4 bytes again, I access every new element by just accessing it unilaterally. And it creates gaps. It does, I mean, it's going to create gaps. It's going to not be efficient. You're right. You're not maximizing the amount of memory storage, but it's going to be way more performant in terms of lookup, which is what we're going to care more about. And then that brings us to the concept of pointers. And I'm just going to run through. I mean, I'm not going to spend, I'm just running through slides at this point because I don't want to spend too much time talking about things we've already talked about. Pointer arithmetic, right? We've already covered. And then the next set of slides would be talking about our GDB debuggers. That leaves us exactly where I want to leave off today so that we can start doing some more demonstrations on how we can use the debugger to take everything we've talked about and make it meaningful. Excellent. Do we have any questions? Okay, well, I will see you all on Tuesday then. And like I said, what I'll do up until then is any problems you were having on the lab, post them in Discord, and we'll reserve Tuesday as a day to talk about the issues we had with lab 1 and walk through solutions of it. And then I'll push that due date so it's Wednesday so that you could use that Tuesday to correct any issues you've had. And if you haven't already, go and find some members who you can work with online. Okay, everyone, have a great day. I'll see you next week.